Morning, one and all. Welcome back to the video lecture series for signals and systems. Today, we are going to discuss about sampling theorem proof. So, now the technology is entire digital technology, but the availability of signals are in continuous time. So, we need to convert a continuous time signal, any signal, whatever the available continuous time signal, for discretization. So, discretization, continuous time signal means both time and amplitude are in continuous. If you see here, it is our original signal x of t. This x of t is amplitude as well as time. Both are in continuous. So it is a continuous time signal, but availability of all physical signals are like this only. Now the idea is we need to convert this signal into digital signal. So the first step to convert this is in digital signal. You go for sampling. So whenever the sampling concept, sampling means converting a continuous time signal into a discrete time signal. Now, in this continuous time signal, what is the idea to convert this continuous time signal into discrete time signal? What is the basic phenomenon? The idea is we know a periodic impulse time. You consider that periodic impulse time with fundamental period Ts, and then if you multiply this Ts, this periodic impulse time with this signal x of t, and then we are going to get a discrete time signal. Now the question is the selection of Ts, this periodic impulse time, it has some fundamental period Ts. So the selection of Ts, is it our choice? Or is it random? Or what is the basic phenomena for selection of this Ts? So that gives the selection of Ts gives sampling theorem. So we will see sampling theorem proof after. Now first see the idea. We have a continuous time signal. It is continuous, both time and amplitude. Continuous means you can get the information on y-axis. If you see an x-axis at any time instant. So that is the meaning of a continuous time signal. Now coming for this, we are considering this periodic impulse time. This periodic impulse time is going to be multiplied with this continuous time signal. So you just multiply this signal. If you observe this periodic impulse time here with some fundamental period, this impulse is going to be repeated. So these impulses are available at 0, Ts, 2Ts, 3Ts, minus Ts, minus 2Ts, minus 3Ts. So it is from, in theoretical point of view, from minus infinity to plus infinity. Now whenever we are multiplying these two, whatever the amplitude we are getting at these impulses, this amplitude still follows the continuous time signal. That is the idea. The amplitudes of these samples are now previously, whatever the periodic impulse time, these amplitudes are 1. Now, if you observe these samples of sampled signal, these amplitudes are not same because these are following, these amplitudes are sampling amplitudes are following the continuous time signal amplitude. So that is the idea of converting a continuous time signal into discrete time signal. Now, coming for this sampling theorem for low-pass signals. Why we are specifically saying this low-pass signal means, usually our signals, our message signals are low-frequency signals. So that's why we're considering that word low-pass signal. Now, the statement of this sampling theorem is, whatever the message signal we're considering, you identify the frequency components present in that signal. You first identify the frequency components present in that signal. So how can you identify the frequency components present in that signal? The only choice to identify the frequency components, just if you apply Fourier transform for that signal, you will get the whatever the frequency components in that signal. After identifying the frequency components, you select the maximum frequency. You select the maximum frequency. So that is going to be play a major role here. Now we need to design a low pass filter with that cutoff frequency. With that cutoff frequency. What is the need of designing a low pass filter here means, if you not pass this signal, message signal through this low pass filter, there may be some addition of noise in the process. So we are going to be select the maximum frequency is one particular frequency. Then we are going to make remaining all process. So because there may be addition of noise, there may be some extra frequency component will present. Then finally, at the receiving end, it is not going to be reconstruct our original signal. So to avoid all these problems, whatever where maximum frequency present in the signal, for that maximum frequency, we are going to be select the cutoff frequency of a low pass filter. So that's why the statement here, if you observe the statement, a band limited signal of finite energy which has no frequency components higher than WH may be completely recovered from its knowledge of its samples taken at the rate of 2W samples per second. So here, the meaning of band limited signal means it is strictly band limited to the maximum frequency component present in that signal. Next, the selection of sampling frequency, that is nothing but sampling interval, is at least twice of the highest frequency component present in the message signal. So in this case, we are assuming the maximum frequency is W. So the minimum sampling rate is sampling frequency is 2W. Once if you select the sampling frequency, and then you will get the sampling interval. Ts is equal to 1 by Fs. So we need to follow this sampling theorem. Then only we can reconstruct our original signal. So that is the, you have observed here, the condition is Fs is greater than or equal to 2W. At least minimum sampling rate is Fs is equal to 2W. It is nothing but Nyquist criteria or Nyquist rate. So for practical cases, Fs is greater than 2W. For theoretical cases, for ideal cases, Fs is equal to 2W. So what is the proof of sampling theorem? First one is this representation of x of t in terms of its samples, because we need to convert this continuous time signal into a discrete time signal. So that's why you need to first convert into continuous time signal, discrete time signal. And then again, we need to recover our original signal from its samples. That is the overall proof of sampling theorem. Whether it is properly recovered or not, we are going to test with the theory. Now in this, the steps are, first x of t, we can define the x delta of t. X delta of t is nothing but just multiplication of this periodic impulse train with the original signal. And then calculate the Fourier transform of x delta of t. And then you find out the Fourier transform of x of t. And you see the relation between x delta of t, x delta of f and x of f. And finally, you can take the relation between x of t and x of nts. Okay. Now, if see first of all, the idea of converting a continuous time signal into this discrete time signal, you see x delta of t, x of t into this multiplication of periodic impulse time. So that's why x delta of t is equal to summation of n equal to minus infinity plus infinity x of t into delta of t minus nts. This delta of t minus nts is a periodic impulse train. This x of t is our original signal. You are just multiplying. So it is the definition of x delta of t. And then if you want to convert into a frequency domain, you need to apply Fourier transform. So apply Fourier transform on both sides. So x delta of t Fourier transform is x delta of f. Now here there is a product of two signals. One is a x of t original signal, another one is a periodic impulse train. So according to Fourier transform properties, a multiplication in time domain, whenever we consider two signals, multiplication of two signals, if you apply Fourier transform, it is going to be get in the frequency domain convolution. So according to that property, now I'm applying the Fourier transform here. The Fourier transform of x delta of t is x delta of f. And if you see this x of t Fourier transform is x of f, this periodic impulse train Fourier transform we need to calculate separately. This concept is already, it is in Fourier series. So you collect the data from Fourier series. Just if you apply Fourier transform for that periodic impulse train, so you will get that formula. It is a Fourier transform of x of t in convolution Fourier transform of this periodic impulse train. So Fourier transform of x of t is x of f. Fourier transform of this periodic impulse train is, it is the formula fs into summation of n equal to minus infinity to plus infinity delta of f minus nfs. Then you substitute that data here. X delta of f is equal to x of f convolution with x of f fs into n equal to minus infinity plus infinity delta of f minus n. According to impulse property, according to impulse properties, if we convolve x of t with delta of t, we are going to get x of t one. So here, the periodic impulse train is now available in frequency domain. Periodic impulse trains are available in frequency domain. It is going to be convolved with the spectrum of original signal. And then if we perform a convolution operation, it is nothing but, according to impulse properties, it is going to be changed into x of f minus nfs. Wherever we have a sample, at that case, we are going to get a spectrum. So that is the meaning. So according to impulse properties, we write x delta of f is equal to fs into summation of n equal to minus infinity plus infinity. X of f convolution of delta of f minus nfs is nothing but x of f minus nfs. So that is going to be right here. We expand for different values of n equal to 0, n equal to 1, n equal to, and n equal to minus 1, n equal to minus 2. It is going to be like that. If you observe this one, it is nothing but a periodic spectrum with a fundamental frequency fs. So the spectrum is now periodic spectrum. Now fs already minimum sampling rate we have selected, that is the 2w. So it is our original signal spectrum. It is roughly, we have not considered any signal. Suppose any message signal if you consider, it is the information is available on low frequency. So that's why we are designing a filter is a message signal shape is like this. So it is just an assumption. So no need to every message signal is not going to be present. The frequency component is the frequency spectrum is like this. So you observe it is strictly band limited to the W. What is the W? Highest frequency form. Then if you see this x of f minus nfs, you see x of f minus nfs. Suppose n equal to 0, x of f into fs. The same spectrum you are going to get. Next, it is delayed at fs. Now you select this fs is equal to 2w. So whenever fs is equal to 2w, now 0 will appear at fs. This plus w is added, fs plus w. This minus w is subtracted, fs minus w. So like that, the spectrum is going to be get like this. So it is a periodic spectrum from minus infinity to plus infinity. I am going to stop this class. We'll see in the next class how to reconstruct that signal.